Welcome to Mathematics Solutions, MMS, and today we're going to look at what we call interpolation. Interpolation. Now, an interpolation is the process of approximating the value of independent variable within a table. Now we have two types of interpolation, or else we have currently we're going to look at two types of interpolation: the Newton forward interpolation, and also Newton backward interpolation. Newton backward interpolation. Now, let us put our consideration for this lesson. We put on Newton forward interpolation. So let us have Newton forward interpolation. So the Newton forward interpolation polynomial, the Newton forward interpolation polynomial the Newton forward interpolation polynomial is given by P of x is equals to f naught plus u, the first forward difference f naught, plus u into u minus 1 all over 2 factorial, the second forward difference f naught, plus u into u minus 1, u minus 2 all over 3 factorial, then the third forward difference, naught, and so forth, where u is equals to x minus x naught all over h, and h is equals to xi plus 1 minus xi. Now, we would like to do an example to see how do you obtain this Newton forward polynomial. And in that case, let us have an example. For the following data, calculate the differences. get the differences, and obtain the forward difference polynomial, and obtain the forward difference polynomial, forward difference polynomial, and estimate f at 0.25. 0.25. Now, let's look at the solution. How do we do this? Solution. The table that has been given here, or the data itself, is, let us first of all have the data. Let us have the data. The data we have been given, we have x and f of x. So in this case, we have 0.1, 0.2, 0.3, 0.4, and 0.5. And also again, we have now the data for f of x. We have 1.4. We have 1.56. We have 1.76. We have 2.0. And also we have 2.28. Now, this data, when you are doing the solution, you arrange in a vertical way. And so that you're going to get on solution, we have to develop what we call the Newton forward finite difference table. And in that case, you're going to have a column for x and then f of x. So for x, we have 0.1, 0.2, 0.3, 0.4, and 0.5. The corresponding values of f of x are 1.4, 1.56, 1.76, 2.0, and 2.28. Now, so to develop the forward difference table or finite difference table, you will simply take this value 1.56 minus 1.4 to get the first difference here. If you take 1.76 minus 1.56, you'll get the second difference. I get the second difference in the first difference. And so we're going to have 1.56 minus 1.4. We're going to obtain, pick the calculator. It will be 1.56 minus 1.4. We'll get 0.16. And then we have 1.76 minus 1.56. We'll get here 0.20. Then we have 2.0 minus 1.76. We get 0.24. And also if you take 2.28 minus 2.0, you obtain 0.28. Now, if you check clearly where I'm writing my values, it's in between 1.56 and 1.4, 1.76 and 1.56, between 2.0 and 1.76 is where we are writing 0.02. This one here we call the first forward difference. So, and since now it's supposed to be a finite difference table, we need to go to the second forward finite difference, F like that. So in this case, still you're going to take 0.20 minus 0.16 to obtain the value here. So you're going to have 0.20 minus 0.16. You'll get 0.04 here. Also 0.24 minus 0.20, you get 0.04. And also 0.28 minus 0.24, you simply also get 0.04. Since we are not yet at the end, so we still continue with the difference table. We have to the third, now this is going to become 0, and this is going to become also 0. And then to the fourth one, the fourth difference, and also the difference will become equal to 0. Now, we are saying the polynomial, the forward difference polynomial is given by P of x is equals to F naught plus U, the first change of F naught plus U into U minus 1 over 2 factorial, then plus, not plus, we have the second difference here, not, and then you have plus U into U minus 1, U minus 2, all this over 3 factorial, then the third forward difference at naught. It continues like that. Now, this one here, the F naught, this one here, the 1.4, is our F naught. The 0.1 is our X naught. Then we have 0.16 becomes the first change F naught. Then 0.04 becomes the second difference F naught. And this one here becomes now the change, that change of F naught. And finally, we have this one here, the fourth difference F naught. So you only need to plug in and substitute into a function where we know that where U is equals to X minus X naught all over H. And you have said that this H is equals to X I plus 1 minus X I. Now let us see what are we going to do in this case. What is it going to happen? So we substitute. Our P of X is equals to our F naught is 1.4. Then plus we have U, our U, we have U multiplied by our F naught. Our first change, the first change, which is 0.16 plus U into U minus 1 all over 2 factorial. Then now we multiply by 0.04. Now, if we go to the next, whereby we're going to have the third difference F naught, it's already 0. And so it means even when you substitute in the formula, it will become still 0. So the same case applies to the fourth difference. So we are not going to write them because already they diminish to become 0. Now, our U is equals to X minus X naught. Our X naught is 0.1. And our H is equals to 0.1 because we can just simply take any two consecutive values of X. For instance, 0.5 minus 0.4, we get 0.1. If you take 0.4 minus 0.3, you get 0.1. Since the intervals are equal, so our H is equal to 0.1. So if we continue now, We are going to substitute our u into the function so that we can have our p of x is equals to 1.4. Then we have now our u, which is plus x minus 0.1, this over 0.1 multiplied by 0.16 plus x minus 0.1 over 0.1. Then we have into bracket x minus 0.1 over 0.1, then minus 1. And all this we multiply by 0.04, and all of it over 2 factorial. So we need to simplify one by one. Let us simplify one by one. Let us simplify this part first, the x minus 0.1 over 0.1 and multiply by 0.16. We simplify. So when we simplify, we're going to have the x minus 0.1 over 0.1 multiplied by 0.616 is the same as to be x minus 0.1 multiplied by 1.6. And so this will get 1.6x minus 0.16 minus 0.16. Now, let us continue. So, this was the part that you have already now simplified. This part here, we have get it is being equal to. So if you can select this part, this is the part we have simplified for this function, this one here. We have that function there, like that. Now we also want to simplify the second part, which is x minus 0.1 over 0.1. And then into this bracket, you're going to have x minus 0.1 minus 0.1 all over 0.1. Then you multiply by 0.04. Now, why are we getting this 0.1? The LCM of 0.1 and this one over 1 will be 0.1. So if I take 0.1, I divide by 0.1, I'll get 1. So I'm going to remain with x minus 0.1. If I take 0.1 and divide by the denominator here, 1, I'll get 0.1. I multiply by 1, I'll get minus 0.1. So that is why this bracket has turned to be like that. And now you're having all these, it's over 2. It's over 2. Since 2 factorial is the same as 2 times 1, which is equals to 2. Now, simplifying this, if multiply this denominator as 0.1 multiplied by 0.1, we are going to get 0.01. So we're going to have, in this case, x minus 0.1. We multiply by x minus 0.2. Then multiply by 0.04 over 0.01. And all this is over 2. Then from there, you're going to have, if you multiply these two, you're going to have x squared, then x squared, then we have minus 0.2 minus 0.1, we get minus 0.3 x squared, then we have 0.1, negative 0.1 multiplied by negative 0.2, we'll get 0.1 divided by 0.2, you get positive, you get plus 0.02, like that. And this one here now multiply by 4 by 4. By this 4, you divide by 2, you get 2. You're going to have something like this. Let me show you. So here you're going to have 0.04. So it is going to become 4. Then over the denominator, which is 2, which will give you 2. So with that, well, now you can have this one as 2x squared minus 0.6 x, and then plus 0.04. Now this squared is not supposed to be there, so we remove this x squared here. Let us remove the x squared like that. So you should remain with 0.3x. When multiplied by 2, you get negative 0.6x, then plus that. Now we can now substitute to our function. So all this we were simplifying. All this we're simplifying the second part. So we're going to have p of x is equals now to 1.4 plus 1.6 x minus 0.16, then plus 2x squared minus 0.6x plus 0.04. Now, from there now, if you put the right terms together and then you arrange this polynomial with the decreasing of power, with the decreasing power, you're going to have 2x squared. If you take 1.6x and you minus 0.6x, you get 1x, and then you have 1.4 minus 0.16 plus 0.04, we shall get 1.4 minus 0.16 plus 0.04. We get 1.08. 1.28. So this is the required polynomial. That's the required polynomial. And we will use this polynomial to estimate any value in that table that you've been given, or the data that you've been given. So in this case, they want us to estimate f at 0.25. So this is the same as to have 2 times 0.25 squared plus 0.25, then plus 1.28. So this one here you get it's 1.655. But if in case maybe you wanted to estimate, maybe suppose you want to estimate, suppose we want to estimate, f at 5.2. We will still use the same polynomial because this polynomial is obeying the data. It has obeyed the data that we have. And so therefore, we are going to have 2 into 5.2 squared plus 5.2, and then plus 1.28. And so this one you'll get what? You'll get 5.2 squared times 2 and plus 5.2 plus 1.8. We'll get the answer being equal to 60.56. Now, if you go back to the question, the value 5.0, 5.2 is beyond this table. And so we say that to estimate the 5.2 is what we call extrapolation. But for 0.25, which is in between here, which is there, 0.25, this is interpolation. And the value of 0.25 must be greater than 1.56 and must be less than 1.76. That will be indicating that the polynomial that you got, it obeys the data. Definitely, now for the 5.2, the value of f of x must be greater than 2.28 because that value is more than 0.5. So that is the Newton forward interpolation with an example. Thank you so much for watching the Math Mike Solutions MMS.